Hi, everybody. This is Mr. Folly, and I'm not writing yet. And welcome to 8.3. We're going to do a little net ionic equations, dissolving equations, all that good stuff. So we're going to start with dissolving equations. So when stuff dissolves, what happens? Okay. Ionic solutions, there's two forms. Ionic solutions, oh my goodness. Ionic solutions and covalent solutions. Okay. Ionic solutions turn into ions when they dissolve. An ionic compound, remember, starts with a metal, or NH4. And remember, if I'm drawing my periodic table, my metals are the area that I'm shading in right here. Not hydrogen, though. All right. So they turn into ions. So KCl turns into, make this a little bit bigger, KCl turns into the K ion, K positive ion, and Cl negative ion. And remember, my ions from the periodic table are found using the columns, right? Etc. All right. AlF3, aluminum is in the +3 column, fluorine's in the -1 column. Okay. Now, when I draw a picture of that, so when I'm drawing that picture, the molecular eye of it, what you're going to see is this is my NaCl, and then this is water. Remember, there's a positive end of water, those are the ears, and a negative end of water, that's the chin, right? I would say water looks like Mickey Mouse. So see all the chins are pointed here, so this must be positive. So this is my Na positive, that's in there because all the negatives are attracted to it. This is my Cl negative in there because all the ears, all the positives are attracted to it. Okay, and that's what it's going to look like. Okay, you're going to break up into your pieces, positive and negative, and you're going to be surrounded by water. If ions form, the dissolving is called dissociating, and the solution is called an electrolyte. Ba-bum. All right, this is important. It's a different quality than the other one has. Covalent compounds, or molecular compounds, or covalent solutions, or molecular solutions, do not turn into ions when they dissolve. Covalent will start with nonmetals and be polar. Now, some gases will, like these are gases. Gases always dissolve a smidgen, okay? So if I have this, when these go into water, again, water looks like Mickey Mouse. So in this case, the water is just going to surround it, and it's going to be a little bit random, okay? So here's a water molecule. I think when I circle my water molecules, it helps me see them as water molecules. Okay, so it's not as the chin is always pointing at it or the ears are always pointing at it. All right. Solution-like mixtures. Gases dissolve in other gases too. Solids can dissolve in other solids, and they make alloys like steel. So these are other types of solution dealies. Our solutions will be something dissolved in a liquid, a gas or a solid dissolved in a liquid. Do make a note, if no ions form, dissolving is called dissolving, not dissociating, and the solution is called a non-electrolyte. Covalent does not dissociate, ionic does. And remember, an electrolyte, where did I put it in there? An electrolyte conducts electricity. And that's why it's called an electrolyte. An electrolyte means it conducts electricity. So that means a non-electrolyte does not conduct electricity. All right. Molarity of ions is determined by the coefficients of the dissolving equation. Okay. So if I have a 3 molar solution of Na2S, which ion has the greatest molarity? So I'm going to write this out. So I have Na2S, and I'm going to turn it into ions. Na positive plus S negative 2. Notice how I need a coefficient of 2 to balance these out. Okay. And over here, I'm going to do the same thing with aluminum bromide. AlBr3. Again, starts with a metal, so I'm going to turn into ions. Al, periodic table says +3. Bromine, periodic table says -1, but I need a 3 here, right? So if I have a 3 molar solution here, if this is 3 molar, this will turn into 6 molar. Notice the coefficient will double it, and this will be 3 molar, right? But if I'm over here, and this is 3 molar, 3 times as much, this will be 3 times as much, and 3 times 3, this will be 9 times as much. Which ion would have the greatest molarity? Bromide. All right. Gases will always be molecular, and they're quite soluble in water. Warmer solutions dissolve less gas, and colder solutions dissolve more gas. That's the opposite of solids. Okay, we did that with the solubility curves. We've seen that before. Gases can make solutions, homogeneous mixtures, with each other. A gas and a gas is almost always homogeneous. Net ionic equations. All right, so here we go. Remember, soluble ionic substances should be written as ions. So anything that's soluble should be written as ions. And we're jumping back to our solubility rules. Okay, this is on the last page. The solubility rules right here. I'm going to refer to them. Okay, so soluble ionic substances should be written as ions. Use the use the solubility rules to determine if a substance is ions or together, solid or precipitate, also called insoluble. K2S. So when I look at K2S, K is group 1. Group 1 ions are soluble. Soluble means write me as ions. Bam, I'm an ion. BaNO3. Nitrates are always soluble. So it's always soluble. I write it as ions. Bam. Okay. So magnesium is not group 1. So look at my phosphates. My phosphate rule is phosphates are mostly insoluble, whereas my PO4s, here we go. Phosphates are only slightly soluble, insoluble for us. So insoluble means I write it together. Together, we swim together. Group 1. So that means it's soluble. So I'm going to write it as ions. Li plus 1 plus P negative 3. Balance the charge. Sodium is a group 1 ion. So that's going to be 3Na positive plus PO4 negative 3. Just want to show you that solubility rule again. Group 1 ions, anything in group 1 is always soluble. The net ionic equation only shows the precipitates and the ions that make up the precipitate. So what you can do is write each aqueous substance. Both reactants and one of the products will at least be ions. The reactants are always aqueous. When the same ion is on both sides, it can be canceled out or removed. Okay? So if we look at this, we're given an example. Na2S plus BaCl2 yields NaCl plus BaS. Okay, so the reactants will always be soluble. So I know I have to write those as ion, 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 ion. Okay? Now I've got to figure out, is NaCl soluble or precipitate? Well, Na is a group 1. Group 1 is soluble. Ion, ion. BaS, barium is not a group 1, so I need to look for a sulfide rule. Dun, 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 dun. Here's sulfide, which is S negative 2. They're insoluble. So if it's insoluble, that means I put it as a solid and I write it together. We swim together. Okay, so now what I do is I cross off the ions that are on both sides. So all I have left is this. Okay, here's my answer. All right, so let's take a look at the next one. You'll be given the equation just like this. Soluble, soluble. Nitrates are always soluble. Group 1s are always soluble. Group 1 or NH4s and nitrates are soluble. This is my insoluble one. Okay. The way I like to do this, here's my little cheating way. I just focus on my precipitate. My precipitate is PbCO3. What do I need to build PbCO3? I need Pb and I need CO3. Let me check those ions. Pb is plus 2. CO3 is minus 2. And notice, my friends, how that is the answer. Boom, 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 boom. So identify the precipitate and roll from there. Okay, let's do one more. Write the net ionic equation for Na2SO4 plus CaBr. Okay, so we would give you NaBr plus CaSO4. Na is group 1. It's going to be aqueous. CaSO4, sulfate rule. Calcium sulfate is a solid. So what am I going to do? I'm going to write calcium sulfate. And I did. And I'm going to write the ions that make up calcium sulfate. Ca plus 2 plus SO4 minus 2. And I'm done. And that's how you write a net ionic equation. Now notice the other ones I didn't care about. Why don't I care about these? They are not part of the precipitate. So that's it. And to that I will say, toodles.